Is Python's Random.Randint statistically random? So I'm testing and calculating the probabilities of certain dice rolls, for a game. The base case if that rolling one 10-sided die. I did 1,000,000 samples of this, and ended up with the following proportions. These should of course all be 10%. There is a standard deviation of 0.03232007% in these results. That, to me, seems rather high. Is it just coincidence? As I understand it, the random module accesses proper pseudorandom numbers. E1s from a method that passed the statistical test to be random. Or are these pseudo-random number generators? Should I be using cryptographic pseudorandom number generators? I'm fairly sure I don't need a true random number generator. See, this URL, this URL. I am currently regenerating all my results with 1 billion samples, cause why not? I have a crunchy server at my disposal, and some sleep to do.
From the random module documentation. Almost all module functions depend on the basic function random, which generates a random float uniformly in the semi-open range, 0.0, 1.0. Python uses the Mersenne twister as the core generator. It produces 53-bit precision floats and has a period of 219,937 to 1. The underlying implementation in C is both fast and thread-safe. The Mersenne twister is one of the most extensively tested random number generators in existence. However, being completely deterministic, it is not suitable for all purposes, and is completely unsuitable for cryptographic purposes. From the Wikipedia article on the Mersenne twister. It provides for fast generation of very high-quality pseudorandom numbers, having been designed specifically to rectify many of the flaws found in older algorithms. If you have an OS-specific randomness source, available through os.urandom, then you can use the random.systemRandom class instead. Most of the random module functions are available as methods on that class. It perhaps would be more suitable for cryptographic purposes, quoting the docs again. The return data should be unpredictable enough for cryptographic applications, though its exact quality depends on the OS implementation. Python 3.6 adds a secrets module with convenience methods to produce random data suitable for cryptographic purposes. The secrets module is used for generating cryptographically strong random numbers suitable for managing data such as passwords, account authentication, security tokens, and related secrets. In particularly, secrets should be used in preference to the default pseudorandom number generator in the random module, which is designed for modeling and simulation, not security or cryptography.
I reran the ops exercise with 1 billion iterations. Here's the reformatted result. See the other answers to this question for their excellent analysis. Martin's answer is a pretty succinct review of the random number generators that Python has access to. If you want to check out the properties of the generated pseudorandom data, download random.zip from this URL, and run it on a big sample of random data. Especially the chi-squared test is very sensitive to randomness. For a sequence to be really random, the percentage from the chi-squared test should be between 10% and 90%. For a game, I'd guess that the Mersenne twister that Python uses internally should be sufficiently random, unless you're building an online casino smile. If you want pure randomness, and if you are using Linux, you can read from /dev/random. This only produces random data from the kernel's entropy pool, which is gathered from the unpredictable times that interrupts arrive, so it will block if you exhaust it. This entropy is used to initialize, seed, the PRNG used by /dev/urandom. On Freebst, the PRNG that supplies data for /dev/random uses the Yarrow algorithm, which is generally regarded as being cryptographically secure. Edit, I ran some tests on bytes from Random.Randint. First creating 1,000,000 random bytes. Then I ran the end program from Formulab on it. Now for the chi-squared test, the further you get from 50%, the more suspect the data is. If one is very fussy, values less than 10% or greater than 90% are deemed unacceptable. John Walker, author of Ent, calls this value almost suspect. As a contrast, here is the same analysis of 10 MIB from Freeb's 0 PRNG that I ran earlier. While there seems not much difference in the other data, the chi-squared percentage is much closer to 50%.
Yes, it is statistically random for all practical purposes. The random variation you saw is perfectly normal. In fact, it would be a poor RNG if it didn't have variation like that. Since the period of the PRNG is 219,937 to 1, you would need to generate more numbers than there are atoms in the universe before you see a non-random distribution. Note that if you generate 623-dimensional vectors, it becomes non-random much sooner.
These results are very close to what you'd expect, and there's a simple calculation you can do to check that. If you roll 1 million d10s and count the number of ones, say, the mean of that random variable is 100,000, number of trials probability of success, and the variance is 90,000, number of trials probability of success probability of failure, so the standard deviation is SQRT 90,000 equals 300. So you should expect to get something about 300 away from 100,000, i.e. 10% plus/minus 0.03%.